So next topic, it is momentum equation. So it is very important equation for our computational fluid dynamics. For first, it will based on principle conservation of momentum principle. So conservation of momentum principle you have studied in your lower classes, that is rate of change of momentum, which provide you some action, that is nothing but your Newton's second law of motion. Okay, so that is nothing but force equal to mass into acceleration. So here this left hand side and right hand side is very important to understand first. This m into a, this is indicating inertia, okay, and this equal to force. So force causing this inertia, it is very important. So which type of forces? So in our lower fluid mechanics, we have studied Euler's equation. In Euler's equation, generally pressure force and gravity force, these two forces we have considered in case of your Euler's equation. Okay, in Euler's equation we have not considered this viscous type of force. Okay, only this body force and pressure force. We restricted our constraint, it is nothing but your body force and pressure force only. We have not considered viscous force here in case of your Euler's equation. But if we again add one force, it is nothing but viscous force. So it will be our Navier-Stokes equation. It will be our Navier-Stokes equation. So first we recall our some concepts of fluid mechanics. So there are mainly two types of forces occur in our fluid mechanics: body force and surface force. So what is body force? We check directly on volumetric mass of fluid element. So the body force always act on your complete body, or we can consider complete volume. Let us assume our body force, if we are to consider, so weight concentrating at center of gravity. So that weight, it is nothing but your body force, one of the body force. Second important body force, it is electromagnetic force. Okay, so electromagnetic force is also body force which act on complete body. Okay, similarly our buoyancy force, this is also body force. Okay, so next important surface force which act directly on surface of fluid element. Okay, just like your shear force. But mainly first primary surface force, it is pressure force through which fluid will act or fluid will flow, we can say. So fluid flow possible due to pressure difference only, we know it already. So that's why pressure is must. So that's why first primary our momentum equation, Euler equation, we have to consider pressure. Then only we can make our momentum equation. We can skip this viscous force for ideal cases, but we cannot skip this pressure force. So pressure force which distribution act on the surface imposed by outside fluid surrounding the fluid element. Always remember, pressure force direction is compressive in nature. It will not be tension. It will always be compressive in nature. Second important force, it is viscous force, which we have not included in our Euler's equation. In Navier-Stokes equation, we have included this viscous force. So here normal and shear component distribution stress act on fluid element, also imposed by outside fluid. Okay, so this is viscous force which we include in our Navier-Stokes equation. So we start our Navier-Stokes equation. In simple way, I will take this complete Navier-Stokes equation step by step. If we follow, then it will be very easy. Okay, so first let us assume infinitesimal small element. For your understanding, I am making this diagram bigger inside, otherwise it is very small. Okay, remember whenever I am writing tau, so there will be two terms. First term indicate plane and second term indicate direction. Always remember, first term indicate plane, second term indicate direction. So first normal direction. So first I start with normal direction. So first I am considering momentum equation for x direction. Remember, I am here considering x direction only. So second term, this will be x, always x. So first term will be x, y or z. It may be x, y, z. Remember, For x direction momentum equation, if I have to write, so second one it will be x, because for x direction second one will be x only. For plane it will be x plane, y plane and z plane. So first x plane. So x plane will be what? This will be your x plane. So tau x, it is normal to the x plane. X plane, x direction. Okay, x plane, x direction. Remember, this is our origin. So from origin we are taking this initially. So tau xx into, in which plane area this tau xx is there. So this is nothing but dz and dy. So dy, dz, this will be your area where tau xx normal stress will be there. Okay. In fluid dynamics, this is generally we neglect. Okay, for normal plane it will be not very much important here, because mainly our pressure force will be dominant over normal here. So here tau xx, if I have to write change, so it will be in x direction change. With the help of Taylor series expansion, I will write tau xx plus del by del x of tau xx dx into area of cross section, it will be dy dz. Second important thing, that is y plane and x direction. Where is origin? Origin is here. So y plane is where? This will be your bottom one, y plane. So this will be your y plane. So y plane. So y plane, this will be your y plane, tau y x and dx into dz. This will be your surface area, dx into dz. So for complementary, there will be some change in y direction. This tau x will get changed in y direction. So y direction change, del by del y, tau yx into dy. And area, surface area is what? Dx into dz. Dx into dz. Okay. So third one, that is nothing but z plane and x direction. Where is origin? This is origin. So I start with this. So origin I am starting. So this is our origin. So this is tau zx dot. What will be your area? Surface area. Z plane. Dx dy. Dx dy. And similarly for complementary, for this will be this tau zx plus del by del z, where the change will occur in z direction. So that's why del by del z, dz. And then area of cross section. What will be area of cross section? Dx dy. Same, just like in continuity equation we have write net force. Okay, there net mass. So here net force acting in x direction. Net force acting in x direction. How I will write net force acting in x direction? Same. This minus this, then this minus this, similarly this minus this. This will be net shear force acting, okay, in x direction. Same, at the same time there will be pressure force. So pressure, where is origin? So near to origin pressure Px. So where, in which direction pressure? In x direction, dy into dz. X direction area cross section, dy into dz. Same pressure change will be Px plus del by del x of Px dy dz. Okay. Sorry, this will be dx and dy dz. So now, up till now we have taken pressure force, up till now we have taken all surface forces. Next, gravity force. So for gravity force, body force, generally here if we are taking x direction, so net body force will act on y direction. But if I have to write complete body force, so for complete body force it will be Fx dx dy dz. So this is per unit mass basis, Fx dx dy dz. Okay, so this is all about your all the terms here I have included. So I write this complete equation. So for density I multiply, sorry. Okay, so this is per unit mass, body force in x direction per unit mass. So that's why I multiply rho into dx dy dz. Rho into dx dy dz is what? Mass. So that's why it will be body force in x direction per unit mass. Okay. So now I write this complete part in one sentence. So what will be net pressure force? Net pressure force. So net pressure force is what? This is our direction. So x direction, take positive. Okay, positive x direction, this is negative x direction. So positive x direction is px dy into dz, minus negative x direction it will be what? Px plus del by del x of px dx dy dz. So these two will cancel out. Finally, what will be remaining? Minus del by del x px dx dy dz. So this is net pressure force in x direction. Similarly, net surface force in x direction. So net surface force in x direction, because pressure force is also surface force, so I include this minus del by del x of px dx dy dz. Similarly, I have to include viscous forces also. So viscous forces will include tau xx, tau yx, tau zx. So how I will write this? Del by del x tau xx plus del by tau xx plus del by del x of tau xx dx. This is what? Dy dz minus tau xx dy dz. So see the direction. Okay, so this is nothing but your positive direction, this is our negative direction, this is positive direction and this is negative direction. Okay, so that's why this is negative direction, because this is near to origin. Okay, tau xx, and this is change in x direction. In previous diagram we have seen this. So finally this is for tau xx. Similarly for tau yx plus del y of tau yx into what will be your dx into dz, surface area. Okay, so common. So this is dy minus tau yx into dx. Similarly for your z direction, so for z direction tau zx plus del by del z tau zx dz, then this will be your dx dy minus tau zx dx dy. Finally these two will cancel out. Okay, so our all forces, step by step I will write. This is our inertia force. I have previously explained you mass into acceleration. It is equal to what? Pressure force, viscous force, gravity force. What is pressure force? Net pressure force minus del p by del x. Okay? So it is minus del p by del x. Dx dy dz will be common. So everywhere I have to write this. So I will common this dx dy dz. Okay. So plus del by del x of tau xx, second term, plus del by del y of tau yx plus del by del z of tau zx, and common it is dx dy and dz. So this is all about your viscous, this is pressure, and what is gravity force? So gravity force it is plus rho f of x dx dy dz. So what is left hand side now? Mass. So density into volume, dx dy dz into density. It is nothing but your mass. Okay. About acceleration, so total derivative of velocity in x direction. This is nothing but your inertia. So dx dy dz, dx dy dz, dx dy dz. This complete term will cancel out. Du by dt. It is equal to minus del p by del x plus del by del x tau xx plus del by del y tau yx plus del by del z tau zx plus rho f of x. This is your Navier-Stokes equation for x direction. Similarly for y direction, if I have to write, so this will be your for y direction del p by del y plus del by del x tau xy. Now direction will be y every time. Del by del y tau yy plus del by del z tau zy plus rho f of y. Okay. Similarly for z direction, this will be minus del p by del z plus del by del x tau xz plus del by del y tau yz plus del by del z tau zz plus rho f of j. See, this is our complete Navier-Stokes equation for this infinitesimally small element moving with fluid. So that's why it is non-conservative in nature. Remember, this is non-conservative in nature and partial differential form. Okay, so we can convert this form into conservative also if finite control volume fixed in space. So this will be your pressure term, this will be your diffusion term, this will be your body force term, and this will be your inertia term. Okay, so how we can split this into convective term and then conductive term, and then how we convert this momentum equation in energy equation, later on we will see. Okay, thank you very much.